All right, we'll get started today. So, good morning, everyone. So we're moving on with other topics in chapter 5 related to moles. And the first thing we're going to start with is, if you recall, we did at the end of last time, we learned how to take a chemical formula and determine the mass percents of the elements from that. And today we're going to learn how to work backwards and do it the other way, where we give you the mass percents of the elements, and then you can use that to determine, at least part way, to a chemical formula. Now, the first thing we have to understand, though, is that when we do that, if we have mass percents of elements and we try to determine the formula, we can't actually get the full molecular formula. We get what's called the empirical formula. So in a covalent compound, the molecular formula is the total number of each atom in a molecule of the compound. And that's how we would typically report the formula for covalent species. So that's the typical, when you look at a molecular formula, that's what it has. And that's what we talked about. That's one key difference between covalent compounds and ionic compounds. Ionic compounds, you always report the smallest whole number ratio of the ions, but for covalent compounds, you report the actual number that would be in that whole molecule. But then what we also have is the empirical formula, which would be that lowest whole number ratio. So for ionic compounds, the empirical formula and the actual chemical formula are the same. That's how we report it. But for covalent compounds, if you have the ability to reduce the ratio, you can get what's called the empirical formula as well. So just again to emphasize, if when we did ionic compounds, we talked about how we always want that smallest whole number ratio. So for ionic compounds, the empirical formula and the ionic formula are the same. But for many molecular formulas, if they can be reduced, if the coefficients, the subscripts can be reduced to smaller whole number ratios, you would have then a different empirical formula. So as just some examples of how this would look, if we have the compound N2H4, which is called hydrazine, we see that is reported with 2 nitrogens for hydrogens. The greatest common factor of those would be 2, so we could divide everything by 2 and get an empirical formula of NH2. For H2O, though, which is water, there is no way to reduce that formula down. So the empirical formula in this case would be the same as the molecular formula, because you have a subscript of 1 in oxygen. You can't divide by anything bigger than that. So for water, H2O, you would just have the empirical formula and the molecular formula being the same. That certainly can be true if your molecular formula represents a smallest whole number ratio. If we go to benzene, which is C6H6, that hexagon-shaped molecule we talked about at the end of chapter 4, this one has coefficients or subscripts of 6 on each of the atoms. So we can divide both of those by 6 and get an empirical formula of just CH, one of each. And then for this one here, you have P3N3H6. The greatest common factor of 3 and 6 would be 3. So if we divide by 3, we get BNH2. So empirical formulas are going to still be whole numbers. You don't want to have fractional subscripts in them. But to get an empirical formula from a molecular formula, you always just want to divide by the greatest common factor of all the subscripts. Now, empirical formula by itself is not super useful in most cases, but the reason we're introducing it is because if mass percent is your input, if that's what we're giving you, here's the mass percent of all the elements in the compounds, what you will be able to get from that is the empirical formula. You would need additional information to get the molecular formula, as we'll talk about. But if you have the mass percents of all the elements, you can convert that into an empirical formula. But any multiple of that empirical formula would have the same mass percent. So you can't distinguish different multiples of that from just the mass percents alone. As I said, you would need additional information to do that, as we'll talk about. But let's talk about then how we actually go about that. So if we have the mass percents of each element in the compound, as we talked about way back in chapter 1, that's one of the earliest and simplest ways to categorize the composition of substances, is to give mass percents of each element. What we basically do is, if we have the masses or the mass percents of each element, we convert those masses into moles. So we're going to have either a mass or a mass percent of each element that's going to be converted to moles. We use the atomic mass to do that, as we introduced last time. And then we're going to have a number of moles of each element, and we're going to convert to the lowest to the smallest ratio by dividing by whichever of those is the smallest. So each molar quantity that we get is going to be divided by the smallest of those to get them down to a ratio. And then this last step, step 3 here, is only if necessary. Sometimes when you do this, first 2 steps, you won't always get whole numbers for all of the subscripts. You'll get sometimes decimal or fraction numbers. So then what you need to do to fix that is you would multiply all of them by some small factor to remove the decimal or fraction. So one common mistake that people make in these problems is they do too much rounding. They'll get numbers that are like kind of far off from a whole number, and they'll just round it to the nearest whole number. But you want to actually think about it as a decimal. And so, as an example, if you do these first 2 steps, you get a empirical formula of C0.5H. So if you have 0.5 in any of your subscripts, you would want to multiply by 2 to get rid of that. You don't want to round it up. You want to multiply by 2. So that would multiply by 2 and become CH2. You have to multiply both of the subscripts. You have to keep the ratio the same. I don't want to change the ratio. Or if we got something 0.333. So for example, if we had N 0.333H, if you see that, again, you don't want to round it up or down. You want to multiply by 3 to get rid of that decimal, and that becomes NH3. Okay. So you won't always see this. I'm not sure if any examples that I have include that step, but if you see decimal numbers, unless they're really close to a whole number, unless they're like 0.99 or 0.01, really close to that whole number, where it's fine to round them. But if they're, you'll typically see things like I said, 0.33 or 0.67, you want to multiply by 3 to get rid of it. If it's 0.5, you multiply by 2. If it's 0.25 or 0.75, multiply by 4. It's not usually going to be much more complicated than that, but don't do too much rounding. That's a common mistake that people make. All right, so let's do the first example. So this one here is just in terms of raw masses. So we have a compound called vanadyl chloride. It's an interesting compound because it's a metal compound that exists as a liquid. Most metal compounds are solids. So you take a sample of this and determine that it has 1.47 grams of vanadium, 0.462 grams of oxygen, and 3.07 grams of chlorine. What is the empirical formula? So in this setup here, we're giving you the actual masses of each element in the compound, not mass percentages, although the way we treat those is basically the same. So what we're going to do then is we're going to take each of these masses and first convert them into moles. as I said, that's typically the first step in this chapter, convert into moles whenever possible. So we're going to do that for each of the three elements. So for vanadium, we have 1.47 grams. And we want to convert into moles and cancel out grams. We need to find the atomic mass of vanadium, and we're going to actually end up dividing by that to cancel out grams. So if we go to the periodic table, V is right here towards the beginning of the transition metal series, and it has an atomic mass of 50.94. So we'll use that number for vanadium, 50.94 grams in 1 mole. So grams cancels out, and that gets us 0.0288 moles of vanadium. For oxygen, we're going to do the exact same thing, but using its mass and atomic mass. 0.462 grams of oxygen. And then we have to find the atomic mass of oxygen, which is one we'll see a lot, 16, pretty much exactly 16, right there, number 8. So we're going to use that atomic mass to convert into moles for oxygen, 16.00 grams of oxygen in 1 mole. And we get basically the same number. I think depending on how you round it, might be a little bit different, but we get almost the same number for that. And then when we do chlorine, we have 3.07 grams. So we're going to do the same step for however many elements we have in the compound. Probably not more than 3 in most cases, but you could do it for any type of compound that has 2 or more elements. 35.45 grams per mole for chlorine. So that's the atomic mass we'll use for that one. So this number we get is a bit different, 0.866. So then once we have the 3 amounts in moles, we want to get them into a ratio so that that can be written as an empirical formula. So what we do is if we're okay with decimal coefficients, we could just write it like this, although this is a non-standard way of doing it. But we don't want those decimal numbers as our subscripts, so we're going to divide each of those subscripts by the smallest one, which is 0.288. So when we divide those out, that comes out to 1 for vanadium. Oxygen, you might get like 1.01 or 1.001, but it's close enough to 1 also. And then those two numbers divided, 866 and 288, divide out to 3, so you would get VOCl3. In this case, we get whole numbers directly, so we don't have to do anything else to fix that, and that's going to be our empirical formula for that compound. That also is the molecular formula for what it's worth, but for masses of elements or mass percents, we only can know the empirical formula, and that's as far as we can get here. So any questions on that? Yeah. I mean, as far as sig figs go, it's not gonna come up as much the rest of the course. I mean, when you're doing it this way, you're trying to get to whole numbers anyway, so you don't want to round too much. I would still keep 3 or so sig figs when possible, in your intermediate steps, but you're gonna get down to whole numbers anyway, which don't have sig figs, so you're fine either way. All right, so then the next one is one that involves mass percents. So it's almost exactly the same. So here we want to find the empirical formula for a binary compound consisting of boron and fluorine that is 15.94% boron by mass. So this one we don't have nearly as much information, so how do we proceed? The first thing is to realize that this keyword here, binary, we've seen it a few times before, means there's only 2 elements in the compound. So boron and fluorine are the only 2 we have to worry about. There's not a third one in this case. And we're given just the mass percent of boron is all we have. So what we need is also the mass percent of fluorine. We should recognize from law of conservation of mass, from things we learned a long time ago, that the sum of the mass percents of the elements should equal 100. So if we know that boron is 15.94%, the rest of that 100% would be fluorine. So we can get that very easily by subtraction. Mass percent of fluorine is going to be 100% minus the mass percent that we have for boron. So it comes out to 84.06%. All right, so that's going to be the mass percents that we have. We have a mass percent for boron here, fluorine there. So how do we deal with these in terms of converting into moles and getting a smallest ratio? Because we're not giving you grams of substance here, we're giving you percentages. Well, whenever you're given percentages, the easiest thing to do is just to assume that you have 100 grams of that compound, because as we said, those percentages are going to apply no matter how much of the compound you have. So if we're given mass percents as our input, we'll assume that we have 100 grams of the compound, and then those percentages would just be the number of grams of each element we have in that 100 grams of compound. So we're going to assume we have 100 grams of compound, and then from there we can get the masses very easily, because in 100 grams of this compound, we would have 15.94 grams of boron, 84.06 grams of fluorine, and then we can just follow the exact same steps we did, convert each of them into moles, and then normalize to get them into a ratio. So for boron, in a 100-gram sample, we'd have 15.94 grams of that element. And we're going to divide by the atomic mass to get moles, so we need to look those two up. Boron is 10.81, fluorine is 19, so those are the two atomic masses we'll need for this problem. So we have 1.474 moles of boron, and then for fluorine, we're still assuming we have 100 grams of the compound, so the mass of fluorine in 100 grams is 84.06. We looked up the atomic mass of that one to be 19.00. So we get 4.424. So those are the moles of each element that we have in 100 grams of the compound, and then the ratio of those would give us the empirical formula. So B 1.474, F 4.424. Clearly not whole numbers, not anything close enough to round, so we're going to divide the two numbers. That comes out to BF3. No need to further modify that. All right. So it's the same steps. It's just when we're starting with mass percent, we assume that we have 100 grams, and then those percentages can be thought of as just how many grams of each element we would have in 100 grams of that compound. All right, so any questions so far? All right, so we're going to now talk a little bit about what else do we need if we're going to get the full molecular formula. So this method where we have masses of each element or mass percentages can only get us the empirical formula. But if we want to find the molecular formula, what we also need is the molecular or the molar mass. So what you would have is you're going to have your empirical mass, which comes from the empirical formula. That's the sum of the atomic masses in the empirical formula. The molecular mass would be given to you, and then you're going to find some small whole number factor that relates them, and that's what you're going to multiply your empirical formula by. So as an example of how this works, let's say we do all the steps we just covered, and we get an empirical formula of CH2. We want to know what is the molecular formula if the molecular mass is 70 AMU. So the way we're going to handle this is we're going to figure out first what the empirical mass is. So our empirical formula is CH2, and the empirical mass is going to be just the sum of the atomic masses in the empirical formula. So we have one carbon in the empirical formula, which is 12.01 AMU. That's from the periodic table. We have two hydrogens in the empirical formula with an atomic mass of 1.008. So we don't need that much precision here because our molecular mass is just given to two places. So we'll just do that as well. So 14 AMU is the empirical mass, and the molecular mass is given to us as 70. So what we're going to find out next is what is the factor then that relates the empirical formula and the molecular formula by dividing the two. So if we take the molecular mass and divide it by the empirical mass, we have 70 AMUs for the molecular mass. That's typically going to be given to you in a problem like this. There's no way to figure that out separately if you don't know the formula already. I think the sound is some sort of construction or repair work going on. It's been annoying us all semester, but we'll get through it. All right, so basically the factor that relates those two is 5. And so what that tells us is that the molecular formula, which could be any whole number multiple of the empirical formula, in this case is going to be 5 times the empirical formula, because the masses are related by a factor of 5. That means the formulas have to be related by a factor of 5 as well. So our empirical formula was CH2. We multiply that by 5 to get a molecular formula of C5H10. All right, so that's just the one additional step you would need if you want to figure out what the molecular formula is. If you know the empirical formula and you know the molecular mass, you just have to relate those by a factor and multiply the empirical formula by that same factor to convert it into a molecular formula. All right, so let's do one example then that puts all of that together. So we have a compound given here that is 28.18% in manganese by mass, 30.80% carbon, and 41.03% oxygen. Those are all mass percentages, and they add up to 100. They should, yep. And the molar mass is 39.98. So what is this molecular formula? So in a problem like this, we're going to combine all the steps that we've already learned. We're going to assume 100 grams of the compound for each of these into moles, find the empirical formula that way, and then relate the empirical mass and the formula mass as well. All right, so this is going to be a lot of tedious work, but we'll get there. So if we have 100 grams of the compound, we're going to find the moles of each element. So we have 28.18% manganese, which means 100 grams of the compound has 28.18 grams of that element. So we need to look up that number on the periodic table for manganese, which is Mn. So it's 54.94 for manganese, which is atomic number 25. So 54.94 grams of manganese in 1 mole. That's its atomic mass. So we get 0.5129 moles of manganese. For carbon, we have 30.80 grams. 38.80% is the mass percent. We're assuming 100 grams. So we have 30.80 grams of carbon. Its atomic mass, which we've seen many times already, is 12.01. That's 2.564. And then for oxygen, 41.03 grams. (16.00 grams per mole for oxygen. So it comes out to also the same number, 2.564. All right, so then that's going to be the moles of each element in 100 grams of the compound. The empirical formula would be the smallest ratio of those, which we can get by just dividing them. So we have manganese 0. I'll just round a little bit because we don't need that many decimals to get this right. So rounding each to just 3 significant figures is plenty for now, just to get the ratio. So we divide all of those by the smallest, which is 0.513. And what we should come up with is manganese C5O5. All right, so that's the empirical formula. It's the smallest whole number ratio. It comes out as whole numbers, so we don't need to do any additional multiplication. But what we're looking for here is the molecular formula, and we also are giving you the molar mass. So that's the second step we have to do now, where we have to relate the molecular mass to the empirical mass to figure out what factor do we multiply our empirical formula by. Now, it's certainly possible that the empirical formula is the molecular formula. It's not exclusive that that can't be the case, but we do have to figure out what's the empirical mass and compare it to the given molar mass. So our empirical mass, we have in our formula 1 manganese. Manganese has an atomic mass of 54.94, which we use up above. 5 carbons, which has an atomic mass of 12.01. 5 oxygens, which has an atomic mass of 16. So what we get is 195.00. So when we divide those two, the molar mass and the empirical mass, if you're good at math in your head, you can already tell what this number will be. It should always be a small whole number. If it's not, that probably means you made a mistake somewhere in either getting your empirical formula or your empirical mass. But our given molecular mass is 389.98. The empirical mass we just found is 195. And to a good approximation, that is a factor of 2. So those are related by a factor of 2 to each other, which means that our molecular formula is going to be 2 times the empirical formula. So we take this whole empirical formula and double it to get the molecular formula. We double every single subscript, not just one. We do all of them. And that gives us a molecular formula of Mn2C10O10. All right. So those are the 2 steps you would need. As I said, it can be a little bit tedious. You have to do a lot of conversions into moles, a lot of arithmetic to get there, but those are going to be the common steps. So any questions on that? Yeah. Yes. So if it asks you to stop an empirical formula, this is what you would report. But if it wants the molecular formula, you have to make sure you compare that to the given molecular mass and the empirical mass to figure out if there's a factor you have to multiply by. All right, anything else? All right, so then the next related topic we're going to talk about is called combustion analysis. We're going to add more steps to this now. So this is a common method that people use to determine the empirical formula of an unknown compound. It sounds pretty crude. You just take a compound and set it on fire. But what you're doing is, we haven't talked a lot about combustion yet, but when you combust an organic compound, you burn it. All of the carbon that's in that organic compound comes out as CO2. So whatever carbon was in there is going to be formed as carbon dioxide as a product. Whatever hydrogen was in the organic compound will come out as water as a product, water vapor typically, since you're doing these at high temperature. And then if there's any other stuff in the compound, you would kind of get that by difference. So most organic compounds are mostly carbon and hydrogen, maybe one other element in there we could analyze as well. But this is how you would analyze it. So the way that this works is basically we're going to measure the mass of CO2 that's formed during the combustion reaction. So we burn the product and measure how much CO2 forms as a product. And we're going to use that to extract how much carbon was in the sample. All right, so we're going to have our mass of CO2 is going to be used to extract how much carbon is in the compound. From H2O, we're going to get the mass of hydrogen. And then if there's any other elements in the compound, those are going to be done by difference. Now you can really only do this exactly if there's only one other element, but basically you're going to know the total mass of compound that you're burning. You weigh that out ahead of time. You figure out from the CO2 and the water that is formed how much of that compound is carbon, how much is hydrogen. The rest, whatever's left over, would be your other element. So you're going to subtract out the mass of carbon and subtract out the mass of hydrogen. If your compound is a hydrocarbon, which means it only has carbon and hydrogen, then you don't have to worry about this step. But if it's carbon hydrogen with one other element, you have to do this to figure out the mass of the other element. Very often the other element would be oxygen. You can't directly measure oxygen because you're burning these compounds in the presence of oxygen. So the oxygen that is in CO2 and water is going to not only come from the compound if it has it, but also from the air that you're burning it in. So you can't easily measure it. So you have to do it by difference in this case. All right. But this is a technique that allows us to determine the empirical formula of an unknown compound. If it's combustible and if it's an organic compound that's mostly carbon and hydrogen, this is a common technique that's used. Now, most often the way this is actually used in chemistry today is more as confirmatory. So you already have an idea of what your formula is, and you use the combustion analysis to both confirm that the formula is what you expect it to be, and you can also verify that it's high purity and things like that you don't have a bunch of contaminants in there. But nonetheless, this technique does allow us to determine empirical formulas. It's just a slightly more involved process. So we're going to do an example of this here. So we have a compound that consists of carbon, hydrogen, and bromine. So in this case, bromine is the other stuff. It's always going to be carbon, hydrogen, and something else, or sometimes nothing else. But that's the situation we have here. So we're taking 5.00 grams of the compound, and we burn it to give 0.871 grams of CO2 and 0.179 grams of water. What is the empirical formula? So it's a little bit more involved than the mass percent approach that we just covered. Because in that case, you're directly converting masses to moles, so it's just one step. It's just divide by the atomic mass. That's all you have to do. This is a little bit more involved because we have to figure out if we have 0.871 grams of CO2, how much of that is made up of carbon, and how many moles would that then correspond to? And same thing for water. So it's a couple more steps that we have to do. So there's different ways to approach this, but here's the way that I'll sort of show it here. Now, if in reality we don't need we don't always need the mass of each element because we eventually want to get the moles of them, but we need the masses here because we have to use that to determine how much bromine there is. So if it was just a hydrocarbon, if carbon and hydrogen were the only two elements, we could just find the moles of carbon and find the moles of hydrogen, and that would be all the information we would need. We don't need their masses individually. But here we need the masses of carbon and hydrogen so that we can subtract out and get the mass of bromine as our starting point. So, but this series of steps will always work, even if you don't always necessarily do all of them. But anyway, so we have 0.871 grams of CO2. So basically what we're going to do is we have to figure out of this 0.871 grams of CO2, how much of that is carbon. And there's a sort of a three-step conversion that we can do to get that. So the first thing we're going to do is we're going to convert this into moles. That's typically our first step in anything we do. So if we want to convert grams of CO2 into moles of CO2, we need the molar mass of CO2, or the molecular weight as it's sometimes called. So for CO2, we have carbon is 12.01 grams per mole. We have two oxygens, which are 16. So we get 44.01. So that's the molar mass of CO2. So that's moles of CO2. We want to figure out how much carbon is in that sample. So then what we look at is the chemical formula of CO2. It's not working very well. All right, so the chemical formula of CO2 has a coefficient or an implied coefficient of 1 on carbon. So that means for every mole of CO2, we have 1 mole of carbon. That's just a 1-to-1 ratio. That's a trivial step there. And then to get mass of carbon, we multiply by its atomic mass, 12.01 see if this other pen works better. We're going to multiply by the atomic mass, 12.01 grams of carbon in 1 mole. All right, so those are the 3 steps we do. We convert grams of CO2 into moles. We recognize that there's a 1-to-1 mole ratio of carbon and CO2, so that's a trivial step. And then we convert moles of carbon into grams of carbon by using the atomic mass. So what we get is 0.238 grams. All right, so of our 0.871 grams of CO2, 0.238 grams of that is carbon. We're going to do the same thing for hydrogen. It's only a little bit different now. So all of the hydrogen in our compound goes out as water in the product side. So that's the number we're going to start with, 0.179 grams of water. We convert that into moles. The molar mass of H2O is 2 times 1 for hydrogen plus 16, so it's about 18, 18.02 if you want to be more exact. So that's just the molar mass of water. Now when we have to figure out how much hydrogen is in there, we're going to convert moles of water into moles of hydrogen. This is where we have to be a little bit careful because in the formula for water is H2O. There's a 2 next to hydrogen. So that tells us there's 2 moles of hydrogen for every 1 mole of water. So we have to use that factor of 2 there to get that number correct. That's the one part that's a little bit different. And then we're going to use the atomic mass of hydrogen, which is 1.008 off the periodic table, to convert into grams of hydrogen. All right, so that number comes out to 0.0200 grams of hydrogen. All right, so we have those masses of carbon and hydrogen, and then the last step, not the last step, but the last step for now to get the last mass is to figure out the mass of bromine by difference. All right, so we burned 5.00 grams of our compound. Parentheses. All right. And then we're going to subtract from that 0.238 grams, which is the amount of mass of carbon that we found up there. 0.02. Why is this pen not working well today? Mass of hydrogen is 0.02. And then by difference, what we get is 4.74 grams of bromine. Okay. So that was a bit of effort, but we got to the point now where we have the masses of all 3 elements. We have 0.238 grams of carbon, 0.02 grams of hydrogen, 4.74 grams of bromine, and now we're off to the races to do the same set of steps we did before to find the empirical formula, which is to take the masses of each element, convert them into moles, and then find the ratio. So for combustion analysis, it's just additional steps that are needed to find the individual masses of each element. Once you have them, then it's going to be the same steps to get the empirical formula. So we're going to find the moles of each element. So for carbon, we have 0.238 grams. The atomic mass of carbon, which we've already used. Now, in reality, when we're doing this step here, when we're converting mass of carbon back into moles, we're really just undoing the last step that we did up here. We had to get the mass of carbon so that we could subtract it from the total to get the mass of bromine, but we're really just undoing that step to get it back into moles. So that comes out to 0.0198 moles of carbon. For hydrogen, we had the mass of 0.02 grams. The atomic mass of hydrogen was 1.008, so we're just undoing that last step. And that comes out to the same number. And then finally, for bromine, we found by difference that there's 4.74 grams of that element. That doesn't come directly from the combustion data. And the atomic mass of bromine we haven't used yet, so we'll have to look that up in the periodic table. The atomic mass of bromine way over here is 79.9. 90 if you want to be exact. So we're going to divide by that to get moles of bromine. And that number comes out to 0.0593. So those are the moles of each. Then we just have to find the smallest ratio to get it as an empirical formula. So the smallest of those three numbers is the 0.0198. So we're going to divide all of them by that. I'm going to get CHBr3. Okay. So combustion analysis is admittedly tedious. I'm not going to downplay that fact. You have to do a lot of steps to get the same information, but it is a real technique we use, and it follows mostly the things we've already covered, just more steps to get there. All right, so any questions on combustion analysis for that example? All right, so then moving on, we're going to start transitioning into how we use a lot of these same ideas about mole conversions in chemical reactions, where we actually are going to start talking about calculating amounts of substances that are involved in a reaction, amounts of products that are formed, and so on. So the first thing we need is what's called a chemical equation, which is going to be a way of diagramming what's happening in the chemical reaction. So chemical reaction is any sort of chemical process where the atoms and elements and or compounds are reorganized to form new substances. We've seen some examples of these already at some level, but we haven't talked about them in detail. But basically, you have on the left side of your arrow, you have reactants, which are the things that go into the reaction. On the right side, you have the products, which are the things that are coming out. Okay, so the reactants are the combinations of elements or compounds. You can have some of each or either. These are going to be ones that are consumed in a reaction. That's what's going into your chemical reaction. Those are going to be on the left side of the arrow, as we'll talk about. The products are the elements and or compounds that form. So those are going to be formed in a chemical reaction. And then coefficients are going to be not the numbers in the formulas of each, but they're going to be the numbers that are in front of each reactant or product that tells us the relative numbers of moles of each that are involved in the reaction. So each chemical symbol or formula that's in the chemical equation is going to have a number in front of it. If there's no number, it's implied to be 1. But that's going to tell you the number of atoms or molecules or moles of each substance that is going to be reacting in that situation. All right, so that's going to be how we deal with the telling us the relative numbers of each. You can think about it at the atomic level, where it's that number of atoms and molecules reacting, or you can think about it more usefully in most cases at the molar level, where it's that many moles of each substance reacting to form that many moles of each product. And from the law of conservation of matter, which we covered very early on, we have to remember that atoms are neither created nor destroyed during a chemical reaction. So the number of each type of atom you have on one side of the equation has to be the same as the number that are on the other side of the equation. They're going to rearrange to form new substances, but the total number of each that you have won't change. Okay, so that's what a chemical equation is going to have in it. So what we have to learn how to do then, as a key part of this section of the course, is how to balance a chemical equation. How to write out the reactants and the products, put the correct coefficients in front of each to make sure that the number of atoms on each side is the same. So that's going to be critical for doing the problems that we're going to get to, which are called stoichiometry. So we put the reactants on the left and the products on the right. That's the easy part. So sometimes we'll give you directly reactants and products. Sometimes they'll be described to you in words. So you have to sort of do it both ways, but you're going to put reactants on the left, products on the right. And then we have to add coefficients to balance them. Now, this is sometimes um, for one class of chemical reactions we'll talk about in the next chapter, there's a systematic way of doing this. In most cases, it's kind of like a trial and error, guess and check type approach. But what you typically want to do if you're unsure is figure out what is the most complex substance in the chemical equation, one that has the most different numbers of elements in it, and set that to one. So we'll show some examples today where that's helpful. You don't always have to do it this way. Sometimes it's not obvious. There's more than one way to approach it. But if you find one substance in your chemical equation that looks particularly complex, it has a lot of different elements in it, set that to a coefficient of one and sort of balance from there. Then you just have to adjust the coefficients to make sure that the atoms balance on both sides. Same number of atoms on each on the left side of the arrow as on the right side of each element that's in this equation. And even though it's not always necessary to do this, um, conventionally we use whole number coefficients and we use the smallest ratios as well. Um, so if we're asking you to balance an equation and that's like the whole problem, just balance the equation, you do want to make sure you get the smallest set of whole number coefficients as possible. If you're just using a balanced equation as part of a more complex problem, as long as it's balanced, it doesn't really matter if the coefficients are their smallest whole numbers or not. As long as it's a balanced equation, it'll work. It's good to check your work when you're done either way. You have to make sure that the number of atoms of each type on the left is equal to the number of atoms of each type on the right. So checking your work is a good thing to do if you have time to do it, and especially if it's a complex one, that you want to make sure you didn't mess anything up. Now, something that's not so important for this part of the course, but you might see it, so I just want to make sure you're aware of it. In a lot of chemical equations, the state of each matter is indicated. The three that you'll see most commonly for now, there'll be others that we'll talk about in the future, are going to be S for solid. So those will be typically given after the formula of the element or the compound, which will indicate whether it's a solid, if it has an S next to it, L would be liquid, G would be gas. That becomes more important for later chapters that we're going to talk about, but you might see it already, so I just want to make sure you're aware of that. So let's go ahead and balance some just to see how this works. That's one of those things that you just have to practice and get good at. So here we have a combustion equation. So we're burning ethane or was C2H6, one of the components of natural gas, although not the major one. And so we're just writing it out multiple times so we can go through the steps of balancing. You don't necessarily need all of these, but we just want to add the coefficients to get this balanced. So as I said, one good way to start these is to figure out which of the substances is most complex, which one has the most atoms in it. So C2H6 is probably the one that I would set as a coefficient of one. It has 8 different atoms in it, 2 different elements only, but there's 8 atoms, C2H6. So that's the one that I'm going to initially set as 1. Now, whether you did that or not, a good way to balance an equation is to find elements that only appear once on each side of the arrow. Because if that's the case, then you know what their ratio is going to be. Because they only appear once on each side, they have to have the same number on each side. So, for example, we see that in this equation, there's only 3 different elements involved: carbon, hydrogen, and oxygen. Oxygen appears in multiple places. It appears once on the reactant side, twice on the product side. So that's not the one that we're going to start with, because there's going to be different combinations of coefficients here that could balance oxygen. But what we want to balance first are the elements that only appear once on each side. So carbon appears only once on the reactant side in C2H6 and only once on the product side in CO2. So our reactant has 2 carbons in it, C2. We need to have also 2 carbons on the product side, so CO2 only has 1, so we put a coefficient of 2 in front of it. So the numbers in front tell us that that's how many molecules or how many moles are involved. So if we put a coefficient of 2 there, that means we have now 2 carbons on the right side as well as 2 on the left from C2H6. And then similarly for hydrogen, hydrogen only appears once on each side. So we have 6 hydrogens right now on the left side from C2H6. Water is the only product that has hydrogen. Water has 2 hydrogens in it. We need a total of 6. We're going to need a coefficient of 3 to make sure there's 6 hydrogens on each side. So now what we've done is we've balanced carbon and hydrogen. So ideally, we don't want to adjust those coefficients anymore because that's going to throw everything out of balance. And the last thing to do is figure out how much oxygen we need on the left side to balance what's on the right. So on the right side right now, we have 2 times 2 is 4 from CO2, 3 waters, which each have 1 oxygen, so 3 times 1. So we have 7 oxygen atoms on the right. We need to also have 7 on the left. And so to get that, we have to have a coefficient that's fractional here of 7 over 2. 7 over 2 times 2 from O2 would give us a total of 7, which is the same number on both sides. As we said, though, it's not conventional to leave fractional coefficients in there. So to finish balancing this off, what we want to be able to do is multiply every coefficient by 2 to get rid of that fraction. So if you multiply coefficients to get rid of fractions, you have to multiply every single one, or else you're not going to be balanced anymore. So we multiply every single coefficient by a factor of 2 to get rid of the fraction. So this 1 becomes a 2, the 7/2 becomes a 7, the 2 becomes a 4, 3 becomes a 6. So then if we want to check our work and make sure we did it correctly, let's go ahead and make sure that we have the same number on both sides. So we have carbon, hydrogen, and oxygen involved in this reaction. So on the left side, we have 2 C2H6s. So we have 2 times 2 is 4 for carbon. On the right side, we have 4 CO2s. 4 times 1 is also 4 for carbon. So that checks out. For hydrogen on the left side, we have 2 times 6 is 12. 2 C2H6s. On the right side, we have 6 times 2 from water. Coefficient of 6, 2 in each molecule of water. So those two match up. Oxygen's the slightly more complicated one. On the left side, we have 7 times 2 is 14. And then on the right side, we have 4 times 2 from CO2 plus 6 times 1 from water also equals 14. So that's how we would check ourselves. There's 4 carbons on each side of the arrow, 12 hydrogens, 14 oxygens. That's the smallest set of whole number coefficients we can use to balance that equation. All right, so any questions on that? All right, let's do one other one. This time we're going to just, it's not more complicated of a situation to balance. It's just one that we have to actually write out the reaction products that are not directly given to us. So rust, which is Fe2O3, is formed when iron reacts with oxygen. So write a balanced equation for the formation of rust. All right, so we said that iron is going to react with oxygen gas, which is O2. So iron just has a formula of Fe. It's an element. Oxygen gas is O2, and they're going to combine to form Fe2O3, which is rust, as the product. All right, so you will see a lot of word problems like this where the reaction is described to you, and you have to translate it into an equation. So make sure we get used to doing that. So this is the first one of those. The starting point for this is a little bit arbitrary, but this looks like our most complicated species. It has 2 elements, total of 5 atoms in the formula. So we'll set that to 1. So in this product here, we have 2 irons. So we're going to put a coefficient of 2 there to balance iron. We have 3 oxygens. So for O2, we would need 3 halves to make it a total of 3 oxygen atoms. 3 halves times 2 is 3. So that's going to be the set of coefficients that works. But if we want whole numbers, we have to, again, double everything like we did before to make them whole number coefficients. So every coefficient is going to get doubled. So it's going to become 4Fe, 3O2, 2Fe2O3, and that's going to balance everything out. We can check our work again. So on the reactants and products side, we only have 2 elements this time. It's a little bit simpler. For iron and oxygen, Iron, we have 4 times 1 is 4. 2 times Fe2O3, so 2 times 2 is 4 also. So that balances out. For oxygen, 3 O2s, so 3 with 2 oxygens in each is going to be 6. And then on the product side, 2 times 3, coefficient of 2 with 3 oxygens in the formula is also 6. All right, so we can check our work and see that that works also. So that was easier to balance most likely, but also we had to write it out from words. So that's something else you have to get used to. Any questions so far? All right, the last one here. The reason I picked this one, it was one of the first chemical reactions I ever did as an undergraduate researcher. Um, you always remember your first kiss. You also always remember your first chemical reaction, I suppose. So I still remember it to this day, as many years later as it was. Um, so this complicated compound here, cesium-4, rhenium-6, selenium-8, I6. So it's pretty complicated thing. We make it by taking elemental rhenium, elemental selenium, cesium iodide, which is an ionic compound, and then I2, also an element, and we just blast them in a furnace for 800 degrees for about 4 days, and it forms this compound. So write the balanced equation and then determine. I'm setting up the problem like this because this is how they're sometimes going to be done on exams. Because, I mean, in the new system with WebAssign, they can probably actually have you balance equations a little bit better than we could before. So you'll see that in the homework. But sometimes because it's hard to have you write out an entire balanced equation on a test, the way that we would ask it is we would ask you to give the sum of the coefficients, either on one side of the equation or on either. So that's not like that's a very useful number to have the sum of the coefficients, but that's just the way that they'll be asked sometimes on the exam. So I just want to make sure you get used to that. All right, but we have 4 reactants in one product here. So we give a little bit of space for, let's put it underneath here so we have more space. So we have rhenium, selenium, cesium iodide, lowercase s, I2, and then one product that has this complicated formula. All right, so that's our reactants and products. Clearly, this is the most complicated substance in the whole reaction. So we're going to set that coefficient to 1. You don't have to write the 1 there, but I put the 1 there to remind myself that that's going to be our coefficient for that one, and we're not going to change that unless we absolutely have to. So then we look for elements that only appear once on each side of the arrow. So the first two here, rhenium and selenium, and cesium. So rhenium, selenium, and cesium, ReSe and Cs, they only appear once on the left side, and there's only one product, so they only appear once on the right. So we'll start by balancing those. Iodine we're going to do last because iodine appears twice on the reactant side, so we don't really know which combination of coefficients is going to be appropriate for that right off the bat until we balance everything else. So we'll start with, in any order we can do this. So we have 6 rheniums here in the product, Re6, so we need a coefficient of 6 there. We have 8 seleniums, so we need a coefficient of 8 there. And then for cesium, we have 4 in the product, cesium-4, so we're going to put a coefficient of 4 there. So then at this point, we can balance iodine by difference. So we've added 4 iodines already from cesium iodide. 4 times 1 is 4. We have 6 on the product side, so that means we need 2 more from I2. So that coefficient is also going to be 1, because we'd have 4 times 1 is 4 iodines, plus 2 more from I2 is 6, and that's the number that we have on the right side. So that coefficient would also be 1. Again, I'll write it in to remind myself, although we don't need it there. If it's not there, it's just implied as 1. All right, but what this question asks for is the sum of the coefficients. That's the way that we would do it sometimes on exams. So that's why I gave it to you here. So when you're doing this, make sure you don't forget the ones that are ones, because again, the coefficients of ones aren't always written in, but they're implied to be there. So the sum on the left side is 6 from rhenium, 8 from selenium, 4 from cesium iodide, and then don't forget the coefficient of 1 that you have on I2, and so that's a sum of 19. All right, so that's a real life example. You know, first day that I was in the lab as an undergraduate, that's what I was told to do. Balance this equation and then figure out how much of each reactant do you need to make the product that we want. So that's what we're gonna learn how to do now is actually, now that we have balanced equations, how do we figure out what are the amounts of each substance that will be involved, either in mostly in grams for this chapter, but other ways of quantifying things in the future that are going to allow us to relate these balance equations to actual amounts of reactants or products. So any questions on balancing equations before we move on to that? All right, so that approach is called stoichiometry, which you probably all know and love already. Um, but what stoichiometry can be simply defined as is it's an approach for calculating the amounts of reactants and or products that are involved in a chemical equation. Now, the key concepts here are what are called mole ratios. So this is the sort of new step. We're going to take everything we've already learned in this chapter, mainly converting mass to moles is going to be the important one for now. We're going to use that as part of it, but then we're also going to use what are called mole ratios from the balanced chemical equations. And that's where those coefficients in balanced equation become extremely important. So the coefficients in the balanced chemical equation tell us the relative number of moles of each substance that are involved. So what we can do then is we can build ratios that we're going to use as conversion factors that allow us to convert from the amount of one substance into the amount of another. If we have this much of one reactant, how much of the product would form? Or if we have this much of one reactant, how much of the other reactant do we need? And so on. Any combination of those we can build up. So if we have a generic chemical equation, not going to write a real one out for now, 3A plus 2B forms 4D. We can take ratios of any of these coefficients and write them as mole ratios. So we can say that 3 moles of A reacts with 2 moles of B, or 3 moles of A would end up forming 4 moles of D. Or if we have 2 moles of B, we would form 4 moles of D, and so on. So any combination of two coefficients in any order, but either on the top or the bottom, is going to give us a unit conversion factor that allows us to convert from the amount of one substance into the amount of another that's involved in that same reaction. So these are all going to be conversion factors. All right, so these are all unit factors when we take ratios of coefficients from a balanced equation. And so that's how we're going to allow us to, again, convert from amount of one substance into the amount of another. So then what's sometimes helpful is a little flow chart here that demonstrates the process. We're going to expand on this in the future, but for now, this is the way it's typically going to work. So the most common stoichiometry problem we'll do, at least in this chapter, is called mass to mass, meaning we're giving you the mass of one substance, 3 grams of ethane is burned, and then we're asking you for the amount of the mass of another substance that would be in that same equation. So if you burn 3 grams of ethane, how many grams of CO2 would form, for example? So it's mass to mass, giving you mass of one substance, calculating the mass of another substance that would be in that same reaction. So we give you the mass of one substance. We're asking you to calculate the mass of a second substance, which would be either a product that forms or another reactant or any combination of two substances that are in the equation. So we're asking you to go from here to here. Now, there's not a one-step process that allows us to do that because the coefficients that are in a balanced chemical equation, they don't relate to the mass ratios of the substance, they relate to the mole ratios of the substance. So we have to convert mass into moles first. So we're going to use the molar mass of substance A to convert it into moles. Again, the sort of mantra for this part of the course, when in doubt, convert to moles. So we're going to do that first. If we have mass of one substance, we're going to convert it into moles. And then the key step for stoichiometry is going to be this one here. And this is what actually stoichiometry refers to. We're going to use the stoichiometric coefficients, the coefficients from the balance equation to convert moles of substance A into moles of the other substance B. And then if it's asking for the mass of substance B, we can use this molar mass to convert into or out of that. Now, occasionally the starting or stopping point might be a little bit different. If we gave you moles of substance A directly, you wouldn't have to calculate moles from the mass. Or if we asked you to calculate moles of substance B, you would not have to do this last step to get to mass. But this is a pretty typical sequence of steps for mass to mass. Start with a mass of one substance, convert to moles, use the mole ratios from the balanced equation to convert to moles of something else, and then convert that into mass using its own molecular mass. Now, there is a slight variation on this that I want to briefly point out. It's not very useful from a chemistry standpoint, but it does come up sometimes in this part of the course, is to use also Avogadro's number as part of this to compute the number of atoms or molecules of one of the substances. Again, not a very practical thing you usually have to do in real chemistry situations, but we have this relationship also. So if you have moles of either substance, we may also sometimes ask you to compute how many molecules of that substance or how many atoms of that substance were involved in the equation, in the reaction. And so you can use Avogadro's number to do that. So just be aware of that. It's not going to come up all the time, and it's not very useful, as I said, but it would be something you might see. All right. So stoichiometry is best learned with examples. So I'm going to go ahead. I don't know if I have time for all of these. I'm going to go ahead. I think I'm just going to do one example. We'll start with one, see how far we get. All right. So we have this reaction here. So this mixture of HNO3, which is nitric acid, HCl, which is hydrochloric acid, is called aqua regia, which is Latin for water of kings, because it's one of the only substances that can actually dissolve gold. So you can take gold and treat it with that mixture of acids, and you're going to get this substance and release some gases as well. And so what we're looking for here is how many molecules of water are formed when, okay, how many molecules of water are formed when 2.56 grams of gold is completely converted to this product AuCl4. All right, so we're given the mass of gold. We're trying to find how much water is formed, in this case, in terms of number of molecules. So just like any other problem we've done in this part of the course, it's helpful to write out what we're looking for. We're looking for number of molecules of water, and then we have a starting point, and then we're gonna work through a series of conversions until we get to that endpoint that we're looking for. So the number of molecules of water, we have 2.56 grams of gold. So we're gonna convert that into moles first. That should always be your first step in a stoichiometry problem, is convert into moles. And so gold is here. 196.97 is its atomic mass. So your first step in stoichiometry is going to be convert into moles of whatever substance you're given. Here we're given the amount of gold, so we're going to convert into moles of that. And then we're going to use mole ratios to convert moles of one substance into another. We're looking for the amount of water, so that's going to be what we're going to put on top here. Moles of water for every mole of gold. And this ratio is going to come directly from the balanced equation. We write it in this way because we want moles of gold to cancel, and we want to form and get into moles of water. If we look at the balanced equation, which is given to us, we have a coefficient of 2 in front of water. So that means there's going to be 2 moles of water formed for every 1 mole of gold. There's no coefficient here, so it's assumed to be 1. And so that's the ratio we're going to use to convert gold into water. Amounts of gold, and then so that gives us moles. Now, once you get to this step here, this is where you have to look closely at what the question is asking for. If it was asking for moles of water, we would stop there. If it was asking for mass of water, we would actually use the molar mass of water to convert this moles back into a mass. But here we're looking for how many molecules of water are formed. So if you're computing the number of atoms or molecules, like we said, that's where Avogadro's number comes into play. So I'm going to go down to the next line here, and we're going to use Avogadro's number, which says that there's 6.02 times 10 to the 23rd molecules of water in every mole of water. So that gets us to where our ending point is, molecules of water. So we stop there, work out the math, and we get 1.56 times 10 to the 22nd molecules of water. All right, so any questions on that? Now I'm going to stop a little bit early today because we're going to do our first bonus quiz today. So that's why we're ending about 10 minutes or so early. So let me stop the Teams meeting because they don't need to see this part. So we're going to stop recording. All right, so some of you have asked